In the Introduction to Data Analysis using R course, we learned the basics of the R language. The datasets we used were simple, delimited text files. In this course, we will learn when and how to use relational databases to perform data analysis tasks using R. For the examples and labs in this course, we will be using either a locally installed DB2 Express-C version 10.5 on Windows, or we will use a cloud-based database as a service offering known as Blue Acceleration for Cloud. R can be used to perform data analysis on many different types of data. The data can be stored in files, relational databases, clustered file systems, such as HDFS using Hadoop, or data can also be processed as a stream. In this lesson, we will specifically examine why a relational database is sometimes an ideal component of our R data analysis tasks. We will examine important considerations such as data type mapping, data integrity, and security. Let's first consider a situation where R has some difficulty with data. One of the key limitations of analyzing data with R is that the data must reside in memory to complete most of the tasks. If data resides in a relational database, SQL can be used to more efficiently extract subsets of the data for analysis within R. R is able to persist and retrieve data structures such as data frames, but the data is either stored in a binary format or it is converted into a text file. There is no simple method of updating or changing a few observations within a single data frame without loading the data into R and then recreating the data file on disk. When the data is stored in a relational database, individual observations or rows can be easily changed. Relational database servers are designed for scalability and can easily support large data sets. Database servers provide concurrent access to these data sets to multiple users. Therefore, a single database could be used for generating standard summary reports using SQL, and the same database could also be used to perform deeper analysis using R. Relational database servers ensure data integrity, consistency, and security. Any update to the data stored in a relational database must adhere to defined constraints, and updates are wrapped in atomic units known as transactions. Access to data can be managed using data control language statements, such as the SQL grant or revoke statement. Database servers can also be configured to provide a data audit trail to better understand any unauthorized data access. Before we move into the world of relational databases, let's examine how data can be stored and retrieved using R and files. Store and retrieve a single R object, a save RDS or read RDS function can be used. Notice how in this scenario we store the df1 object to a local file and then load the object into a new R object called df2. If you need to persist multiple objects, you can use the save function. There are two examples shown here. They both store an external representation of the df1 and df2 objects in a single file called multi.rda. Persisted objects can be retrieved using the load function. Notice how they are restored as objects with their original names. They cannot be directly associated with a new object. If you wish to preserve all of the data structures in your current R workspace, you can use the save.image function. There are some other useful options available with these save functions, including the ability to compress data as it's being stored. In the Introduction to Data Analysis using R course, we examined various ways of reading data sets into R for analysis. You may wish to review that lesson at some point as you complete this course. Let's examine some terminology differences between R and relational databases. Relational database can be considered a collection of related data that is manipulated using a standard access language known as SQL, or structured query language. A database contains a set of data stored in tables or relations. A table can be considered a similar data structure to an R data frame. The table is given a name. In most database servers, a name consists of two parts. The first part of the name is known as a schema, followed by a period, and then the name of the table itself. Schemas are usually used to group a set of tables within a database, as a single database might be used for multiple applications with multiple users. In R, there are namespaces for function resolution, which could be considered somewhat similar to the use of schemas within a database. Our data frame is usually stored as a table, where each observation is considered a row or tuple, and each variable is known as a column or attribute. Therefore, a collection of observations would be stored as a single table. Relational data access is performed using SQL. SQL standards are well established and fairly consistent among database servers. SQL is a declarative programming language that was initially created in the early 1970s. It continues to be used as it is flexible and powerful. It is important to consider that there are times when R techniques for querying data, such as using the function subset, order, or using conditions within the bracket notation, preferred to using SQL, and other times when the power of SQL is ideal. Here we examine the mapping for numeric data types between R and database servers. The database server has a slightly different set of supported data types. Examples shown here are from DB2 on Linux, Unix, and Windows. Precision associated with R numeric data types can also vary across platforms. The .machine function can be used to examine the platform limits of your R environment. The interface or driver between R and the database server should provide a configurable mapping for data types as data is exchanged between the R and the database server environment. One item to note here is that R double values will map to double data types in a relational database, but some database servers such as DB2 provide more precise numeric data types such as decimal or decfloat. Character data in R will be mapped to either a fixed size character column or a variable size varchar column. Usually logical data from R will be mapped to a single character column in a database. Dates are always a bit difficult to handle within R and within relational databases. We consider using character strings for date or time representations as the information is exchanged between R and the database. If you're querying data from a database, the R driver will automatically detect the data represents dates or times and map the data to an appropriate R class. This is something you should validate once you start accessing data from your databases. Factors should be converted to a native representation, which is usually character or integer values, as it is exchanged with the database server. Once the data has been retrieved from the database server, you can use the factor function to coerce the data into a categorical observation for your analysis task. To conclude this lesson, we should consider the design considerations of relational databases. Relational databases are usually designed to minimize data redundancy and model the relationships between tables accurately. If the data has been modeled well, the consistency of the relationships and attributes are maintained. For example, relational databases can manage dependency relationships between two tables by specifying a primary key in the parent table and a related foreign key in the secondary table or child table. This is often known as declarative referential integrity. These structures have no equivalent options within data frames in R. You may find that the data frame you would like to construct will require data from many different tables. Fortunately, database servers are very efficient at joining tables into a single structure for analysis. Often databases have virtual tables or views defined to simplify this process of reconstructing a full data set. Of course, it is possible to create multiple data sets in R and use the merge function, but this operation is best avoided when a simple SQL join or predefined view object can be used. Thank you for completing this lesson on R with relational